Hey gang, today let's take a look at the photoelectric effect and work with the Rydberg equation to describe the wavelengths of light that are given off by atoms. In 1885, a fellow by the name of Johann Balmer started looking through his spectroscope at the light that was given off by hydrogen gas. And he found that there were 4 bands of visible light, and they were red and blue and sort of a bluish violet color and a pure violet color. After much work, Balmer and some other people determined that what's going on is that electrons like to be in what's called a ground state, which is the lowest shell that they can possibly be in, the first shell. And once the first shell is full, then they'll go into the second shell. And once the second shell is full, they'll go to the third, and so on. It turns out that if we give these electrons energy, they can pop up to a higher shell. For example, they can pop up from the first to the fourth shell or the first to the third shell. They don't really like being up there. They like being in a low energy state. And so the electrons will drop back down. And when they drop back down, they have to give off energy. And they give off energy in the form of electromagnetic radiation. And what Balmer was seeing was electrons dropping down to the second shell and giving off visible light. And so eventually, through the work of many other people, including a fellow by the name of Johannes Rydberg, there was a very interesting equation that was determined. And this equation showed us about wavelengths and relationship to the shells of atoms. The Rydberg equation looks very, very ominous right off the bat. It says 1 over lambda equals RH times 1 over n1 squared minus 1 over n2 squared. And so it looks pretty ominous, but if we just take it bit by bit, it'll turn out to be a very easy formula to deal with. You're already familiar with lambda. That means wavelength. You haven't seen RH before, but RH is a constant, just like we had c, the speed of light, which was always 3 times 10 to the 8th meters per second, and we had h, which was Planck's constant, and that was 6.63 times 10 to the negative 34th joules per hertz. Well, this one, always 1.097 times 10 to the 7th cycles per meter. This number will always be given to you. You don't have to memorize or anything, and you don't have to memorize C, and you don't have to memorize H either, for that matter. You just have to be able to work with it. When we look in this part of the equation over here, we have 1 over n1 squared minus 1 over n2 squared. The n values means the shells. The first shell down here in the bottom is called n equals 1. N equals 2 refers to the second shell. N equals 3 refers to the third shell. This diagram shows the shells as being flat and horizontal, but we're used to seeing the shells being circular, like up here in the top. First shell, second shell. So if we consider an electron that drops from, say, the fourth shell down to the second shell, that means the electron is going from n equals 4 to n equals 2. In this case, 4 is bigger than 2, so we're going to put 4 right here in the place of n equal n2, and we're going to put 2 right here. So the 4 refers to the fourth shell, and the 2 refers to the second shell. And now we just have to square these numbers and work with them a little bit. Back to thinking about Balmer, he worked with visible light, and it turns out that visible light comes when electrons drop back down to the second shell. N equals 2 is what we're talking about. So if an electron drops down from the third shell to the second shell, it should give off visible light. These other two fellows, Lyman and Paschen, they worked with different types of light. They worked with ultraviolet light and infrared light. And it turns out that Lyman's ultraviolet light resulted from electrons dropping down to the first shell, or n equals 1. This is always a big drop, and so the light that's given off when electrons drop down to the first shell is almost always ultraviolet light. Lyman's work was with electrons that drop back down to the third shell, and those electrons falling down to the third shell gave off rather long, low energy waves, which are called infrared light. So let's practice working with the Rydberg equation, shall we? So here's a practice problem. Calculate the wavelength of the photon given off when electrons drop from the third shell to the second. So that would be the first Balmer line right there, dropping from the third shell to the second shell. First thing you want to do is write down the Rydberg equation and then start filling in what you know. RH, the Rydberg constant, is 1.097 times 10 to the 7th meters to the negative 1. And then that's times 1 over n1 squared minus 1 over n2 squared. So we have the third shell and the second shell. So we're always going to put the larger number there, and we are always going to put the smaller number here for n1. So we have 1 over lambda equals 1.097 times 10 to the 7th per meter times 1 over 4 because 4 is 2 squared, minus 1 over 9, because 9 is 3 squared. So now if we turn these numbers into decimals, 1/4 is 0.25, 1/9 is 0.11, and we subtract them, we have 0.14. So now all we need to do is multiply 0.14 times this Rydberg constant. The number that we get is 1,520,000 per meter. We need to solve for lambda, which is wavelength, in meters. Remember that any number that you write, for example, if you're 15 years old, it's the same as 15 over 1. So if we take 1 over lambda equals 1.5 million, we can think of this as being 1.5 million over 1. So we want to solve for lambda. To do that, we have to get lambda by itself and on top. So if we flip this side of the equation upside down, we have lambda on top. But we have to do the same thing to the other side of the equation too. So let's flip this one upside down. And that means we now have lambda equals 1 over 1.5 million, this number right here. We take 1 divided by 1,520,000, and we hit enter on our calculator. We end up with this number. Lambda, the wavelength, is 6.5 times 10 to the negative 7th meters. We look through our spectroscope at this, and I look for 6.5 times 10 to the negative 7th, I find out it's red light. That makes sense because this is a Balmer line, and we know it's going to be some sort of visible light, and it turns out that it's red. It's not a big jump. It's only from the third shell down to the second shell. So red light is not that high energy. If we had done this calculation going from, say, the fifth or the sixth shell down to the second shell, probably we would have gotten a higher energy, shorter wavelength. For example, maybe we would have gotten 4 or 5 times 10 to the negative 7th meters, and that would have been like violet light or blue light. That is today's lesson. It's a pretty short one, isn't it? The topics were photoelectric effect, how atoms give off light, and finally the Rydberg equation. And it all started with Johann Balmer back in 1885, who studied the light given off by hydrogen atoms. And then we talked about excited state versus ground state. The ground state is where the electrons want to be. Excited state means they're up higher. And then we worked with the Rydberg equation, where N was the shell number and RH is a value that's always a constant, and lambda is wavelength. And we discussed just a little bit about visible light coming from electrons dropping to the second shell, whereas ultraviolet light comes from electrons dropping all the way down to the first shell. And infrared light comes from electrons dropping down to the third shell. And so that is our lesson for today. Thank you.